Okay, so in this lecture, we are going to talk about quantization, right? We have previous lecture, we talked about pruning techniques that can help remove the number of parameters in a neural network, right? So the number of weights times the bit width per weight, that equals to the total model size. So one method to reduce the model size is by reducing the number of connections, right? So the other way is to basically reduce the bits, number of bits to represent each connection, okay? So this is the agenda for today's lecture. We are going to first review the data types. How are we going to represent the numbers? int8, FP32, what are they? And then we are going to learn the basic concepts of network quantization. And then we are going to cover 3 types of widely used quantization methods, starting from the K-means-based-quantization, linear quantization, and also binary and ternary quantization. So again, model size are growing really fast, and we want to have a small model size and high accuracy. So memory is expensive. We want to reduce the memory movement. So how should we make deep neural nets more efficient, right? So quantization is a very widely used technique that is orthogonal to pruning. So previously we can have a continuous signal, okay, in this figure. In the time axis, we are sampling in time, and in the y-axis, we are quantizing in space. Okay, so suppose the signal is here, we quantize them to 1, 2, 3, 4, 5 discrete values. Okay, although the signal is continuous, but we have only 5 discrete values in this case. So quantization is a process of constraining an input from a continuous. Okay, this is a continuous. Okay, and otherwise large sets of values. It can be any value. Okay, previously it's a large set of values to a discrete set. Okay, in this case, only 1, 2, 3, 4, 5 sets. On the right-hand side is showing an example of quantizing this image. So this is the original image. Okay. And now we are quantizing them into several pattern types. Given a palette, right? We have only a certain amount of colors, and each pixel can only choose from one of these colors. Okay, it's also called palletization. Okay, so we have only a fixed amount of choices that you can pick for the whole image.
Does the discrete set have to be smaller than the large set, or can you quantize? I mean, I know you can't, but does that fit with our definition here, or is it strictly a smaller set?
For quantization, the one you mentioned is super resolution. Right? You don't have that amount of pixels, but you want to expand the number of pixels. That's the reverse side. Actually, whether that helps with accuracy remains to be a question. But for the speed and storage perspective, that definitely will make neural nets larger. But maybe that helps with some other properties of neural network. Feel free to try that in the following project we can discuss. But usually, when we're compressing the model, it's strictly smaller than the number of original values. So first, let's learn some foundation about numeric data types. Okay, when you are using GPUs, you might have heard about like what is the FP32, FP16, int8, what are they, right? So just this week, Jensen Huang, the CEO of NVIDIA, during this amazing GTC talk, he released the new GPUs, right, which support this FP8 numerical system. So what is FP8? What is FP32? What is int? You may also heard of BF, brain float. What are they? So let's start this journey by walk you through these representations in a well-organized manner, starting with integers. Okay, so you may be familiar with that. They're unsigned, and also they are signed integers. Okay, so this is a representation for this. This is an 8-bit unsigned integer. So the lowest bit is representing 1, and 2 to the power of 1 to the power of 2, etc. Okay. So this number we can easily calculate is 49. So all the numbers are equal. And then in order to introduce this assigned number, okay, we want to dedicate 1 bit, okay, dedicate 1 bit to be the signed bit. two ways to represent them. One is just by using this sign magnitude representation. Okay, the first bit just represent the sign, whether it's positive or negative. Okay? The remaining bits just represent the magnitude. For example, in this case, the sign bit is 1, indicating that this is a negative number. And then we have the remaining bits to represent the magnitude. In this case, it's minus 49. So the range for this case would be 2 to the power of n minus 1 minus plus. You can see the number of range. The range we can represent is actually equal to the number of bits minus 1, since we validated it as 1, would be the sign bit. Okay, so that's why it's minus 2 to the power of minus 1. Okay. So both all zeros and all zeros represent 0. Okay, so we are actually wasting one slot for 0. Okay, so since this is the sign bit, no matter if it's positive or negative, as long as the magnitude is 0, it's 0. So wasted one. And how can we avoid such waste? So we implement we have these tools complement our representation. So the positive 1 actually means minus 2 to the power of 7 in this case. Okay, so we put them together. This number still represents minus 49. So the advantage of this method over this method is that we can seek one more number. So the smallest number it can represent is no longer 2 to the minus 2 to the power of minus 1, but just 2 minus 2 to the power of n minus 1. Okay. So all 0 that represents 0, but it's 1, 0, 0 that represents the smallest number, okay, which is minus 2 to the power of n minus 1. Any questions on the integer representation? So far, so good. Okay, so let's talk about the fixed point numbers. What if we want to represent a smaller number, smaller than 1? Okay, so we introduce this decimal point. So above the decimal point, those are the integers, and below that, those are the fraction bits. Okay, for example, in this example, above the decimal points, we represent starting from 1 to 4, and below the decimal point, starting with half, 0.5, a quarter, 1/8, etc. Okay, so we put them together, we add the corresponding bits, we get 3.0625, represented by this number. Okay, let's see another example. Say this is the decimal point, so we want to add them up together. This is the way to calculate by just having everything starting from 2 to the power of 0. And then we can observe how many bits do we have for the fraction part. Okay, since there are 4 bits for the fraction part, we just calculate them as if this is a pure signed integer, and times the scaling factor, which is 2 to the power of 4. Indicating that actually we are moving the decimal point from here by 4 bits to here, okay? So that we can represent this fractional number rather than 49 in this case. And then let's switch here to talk about floating point numbers, which is widely used for training. Okay, so this is the example of 32-bit floating point number. Contains 3 parts. Okay, so we have sign bit, positive or negative, and then we have 8-bit for the exponent. So what is the exponent? 2 to the power of the exponent minus the bias. And then we have 23 bits for the fraction. Okay, so this fraction bit is also called the significant bits or the mantissa. Okay? Significant bits, mantissa, fraction, they are meaning the same thing. So why do we invent this number representation? Compared with integer, what is the advantage of using this representation? The sign bit 1 plus this fraction bit times 2 to the power of exponent minus its bias. Okay? So since we have 8 bits for exponent in this scenario, okay, so we have the bias to be 127 to the power of 8 minus 1, because we want to represent both positive exponent and also negative exponent. And so for example, all the blue bits are 0. Okay, so here we have total power of minus 127. Okay. So compared with integer representation, what is the advantage of floating point representation? Larger range, exactly. Right? Since this is 2 to the power of exponent, this can represent a much larger range for the number, which is actually quite critical for training neural networks. Okay. When you're training the neural nets, especially during the first couple of iterations, the gradients can vary a lot. Okay, so the range, dynamic range, is pretty large. The largest number, the smallest number, they can differ a lot. So using such floating point representation with the same number of bits, we can have a much larger dynamic range. Okay. So let's see, for example, what number does it represent? 8-bit exponent, 23-bit fraction. So let's calculate what is this number representing. So here we have 125. Okay. So this is for the exponent. Okay. So we want to subtract the bias from this exponent. So that's 2 to the power of -1. And then we have this fraction bits, okay, which is, if you calculate this is on only 1 bit, this is 0.5, 1/4, 1/8, 1/16. So this is actually 0.0625. Okay. So this is 1.0625. It is always 1 dot something. Okay, with this representation. And after that, we can calculate this is the final number it represents. Any questions?
Why do we have the 1 plus fraction? Like, why do we represent it like that? Is there a reason for it? Why do you have the 1 plus fraction? We could not just fraction times 61. That would.
You want to make sure it's easy for the arithmetic units to calculate, and also you want to make sure the range can be covering both a pretty large number or pretty small number. So here is a whole family of different floating point number representations. They have just different bit width for the exponent and also for the fraction bit width. So the most popular is this FP32, that's IEEE FP32 standard representation, which has 8 bits for the exponent and 23 bits for the fraction. So plus this sign bit, totally 32 bits. And the half precision, which is representing 16 bits. So it has 5 exponent bits and 10 fraction bits. Okay, you can see it is shorter exponent and also shorter fraction. And then Google proposed this BF16 a couple of years ago, very recently. So brain float. So the brain float has the same amount of exponent bits, but much shorter fraction bits. And so altogether, it's the same number of bits compared with this half precision. However, it has more exponent bits compared with the fraction bits. So what is the advantage of that? We can represent a much larger range during training. Okay? So for neural networks, the precision, the absolute precision doesn't matter as much as the range. So this is training the precision for getting a larger range. Okay, so that's the motivation for this BF16 compared with half precision to give a larger exponent. A couple of years ago, NVIDIA proposed this TensorFloat 32. Okay, and why is it called TensorFloat 32? It has 8 bits, which is the same as the 32-bit FP32 representation, and the exponent. So the fraction bits is actually the same as the original FP16. So it's using the exponents of the FP32 while using the fraction of the FP16. Okay, so it's a good trade-off between the range and also the precision. So altogether, it has 19 bits. And then AMD proposes AMD MP24. It's another representation which has 7 bits for the exponent and 16 bits for the fraction. Okay, so altogether is 24 bits. So recent years, the industry is coming up with drastically very different and very innovative different number representations due to the workload for deep learning. Okay? It's very hot and getting a lot of innovation in the recent years. In particular, this P8 is coming out, like 8-bit floating point. So this deep learning is very exciting, driving a lot of new innovations for this number representation system. All right, so question? What was the question?
So with the ingredients, right, it's here pretty good. I guess it seems like very good at square value, but it's only using that. So that like working with this one, other 19 this is stored more efficiently or
So 32 here means basically it's the same number of same dynamic range of P32, but different from all other representations. This is the only one that actually doesn't correspond to the exact number actually required. So this one, P24 has 24 bits. BF16 has 16 bits, but this one actually have 19 bits.
But like to follow up, why is 19 bits? Like that is a weird number, right? In memory.
Right. In order to store them, probably there are some very special mechanism behind that.
Okay.
Yeah, it's not fine to line. Yeah. So let's do some kind of calculation, right? What is the following half precision number in decimal? 5 exponent bits, and then 10 fraction bits. This is the half precision, which is actually quite widely used in today's deep learning accelerators for training. Almost no loss of accuracy, about 2x speed up, and saving the GPU memory by half. It's very widely used. Let's have 2 minutes for you to calculate what is this number representing in decimal. And since we have 5 bits of the exponent, the bias is 2 to the power of 4 minus 1. Okay, let's work on this together. So first of all, we have 1 bit for the sign bit. It is a 1, so it's a minus number. And then the exponents, we have 1, 0, 0, 0, 1. So and then we subtract the bias. Okay, since we have 5 bits, the bias is 15. So 17 minus 15, we have 2. Okay, the exponent is 2. And then we calculate the fraction. Okay, so this is representing at 0. This is half. This is 1/4. Okay, so altogether is 0.75. Okay. So the decimal answer would be 1 plus 0.75 times 2 to the power of 2. Okay. So it's actually -7. So let's do another reverse exercise. What is the decimal 2.5 in brain float 16? So in brain float 16, we have 1 sign bit, 8 bit of exponent, 7 bit of fraction, and we always want to decompose it by 1 point something. This is 1.25. times to the power of 1. Okay, so we have one sign bit, and the exponent binary is 1 plus 15. Okay, and the fraction binary are similar to before. We can calculate that. So 0.25 is 0 and 1. So this is half, this is a quarter. So the binary answer is here. All right, so let's continue to talk about quantization. Okay, so there are several methods for quantization. Let's start with the most naive one is, of course, using the floating point number to represent both the weight and also the activation, right? And also we are going to use those floating point arithmetic. Okay. The other way, okay, we have K-means-based quantization. Okay, we have integer weights, floating point codebook. We can encode the weights into several buckets. Okay, and each weight will choose from one of these buckets. Okay, and then we have this linear quantization methods. Okay, so all the computation is in integer arithmetic. And finally, we are also going to have binary or ternary quantization, where the weights only choose from a positive value or negative value, okay, or including 0, which is even more compact. So today, hopefully, we can cover both the K-means-based quantization and linear quantization. The next lecture, or if time even have time today, we're going to cover this binary quantization. So let's start with this example where we have a 4x4 weight matrix, which contains a 32-bit floating point number. Okay. These are all floating points. Okay. But actually, in deep learning, we don't need that high precision. Okay, 2.09, 2.12, 1.92, we can just quantize everything to 2. Okay, 2.0, and we find it doesn't hurt the accuracy. So we have a lab tool that will give you this opportunity to try out on yourself with Cypher 10 data set, playing such manipulation of the weights, okay, quantize them, and approximate them, and observe the accuracy actually doesn't drop. Question?
So precision is kind of doesn't matter for either training or inference. I remember earlier you said like the range method for training, but quantization is
for inference, right? If a network is already trained, you quantize them to lower precision. Above a certain threshold, we don't lose the accuracy for inference. For training, there's also active research pushing below 16-bit, maybe even use 8-bit for training, and people still find that can converge.
What's the lowest anyone's ever really gone? Has anyone ever done something silly like 2 bits, 4 bits?
Yeah, we'll talk about that in the binary neural nets. Only +1, -1. Okay. Yeah, let's start a journey together. So, yeah, so let's just do a K-means clustering to find which weights are similar. So these are similar weights around 2, and these green colors, they're around -1, and the pink color is around 1.5. Okay, so we may as well just do a K-means clustering, find their centroids -1, 0, 1.5, and 2. Okay, in this case. For example, if the weight is 2.09 minus 2.12, we may as well just quantize both of them to 2.0. Okay, so previously we have to store this full 32-bit floating point. Now we can only store only 2-bit index. Why 2-bit? Because we have 4 entries in the codebook. So we can use 2-bit to represent which bucket that these weights belong to. Okay, so this blue weight belongs to the 3rd bucket. Okay, it's 2, therefore we are showing 3 in these locations. Okay, it's a very smart way that we have a tiny little code book. If we use 2 bits, only 4 entries. If we use 4 bits, that's going to be only 16 entries. Okay, very limited amount of workload in the code book. And then we just store the integer value in very low precision to represent each weight. Okay, so finally, after quantization, we get the weight to be something like this. And this is the quantization error by subtracting this weight matrix with the previous weight matrix. And we can find they are relatively small. We're going to show the accuracy impact very soon, but first let's analyze the saving of the storage. In this example, we have 16 numbers. Each one is stored in 32 bits. So altogether, we need 64 bytes. Okay. For the indices, each one is represented by only 2 bits, and we have 16 of them. So multiply them together, is 32 bits equal to 4 bytes. Okay. Each byte is 8 bits, if you remember from 604. We learned those basics. And finally, we have to store this code book since we have only 4 choices. So each one is represented by 32 bit. Altogether, that's 16 bytes. Altogether, we need 20 bytes. We need 20 bytes to store them together, which is 3.2 times smaller compared with the original weight matrix. But this is a very small example. Imagine if this weight matrix becomes pretty large, what should be roughly the compression ratio if we use only 2 bits to represent each number? (16) correct. So the size of the code book could be ignored, right? Only 4 numbers. If the weight matrix is super large, then this is the case where the number of parameters is much larger than n is the number of bits. So to the power of n, this is 4 is the number of values in the code book. So you have n m numbers. So altogether we need 32 m bits. For the indices, we need n m bits. And for the code book, we need 32 bits for each number times to the power of n entries. Okay. So since this number is pretty small, we have only like 16 numbers in the 4 bits. We can ignore that part. So the compression ratio will be 32 divided by n.
But how do you choose how many sets? Is it again if I trying to define?
Yeah, exactly. That's similar to pruning, like sparsity ratio. How sparse should it be, right? And how many bits do you need for each layer? We are going to cover the technique to show. You can imagine the fewer number of bits, the lower the accuracy. Before the accuracy drops pretty fast, that's the point you want to go. Very good question.
Yeah, I think if you're on the road, if you're going to have this configuration, you can set training or intensity. Some will be low, like one or two of the direction and writing of the intensity before if that is crazy.
That's a good point. So we are exactly doing one level in direction. But here, like we mentioned in the first part of the lecture, data movement is expensive, computation is cheap, right? Here we need to only dereference from a register file that has only 4 entries, which is very cheap, right? Compared with what we have to go to the main memory to fetch such a large amount of numbers, right? So here, referencing a register file, which is, of course, it'll be in the cache, right? Will be much more cheaper compared with if you have to go to the main memory, since we have a 32 bit. Now you need only 2 bits. So that's the trade-off is worth it. What's the question?
Overall, this is stay faster because we're saving on the
Yeah, due to you are saving the memory and saving more power. Yeah.
Look at people the register file. Like, as in, what if you choose more simple than just taking a register file?
We'll cover in the later part of this lecture. 4 bits will make sure you have no loss of accuracy. So that's only 16 numbers. Of course, can fit to the register.
Does the distribution of weights statistically make a difference here? If you have a Gaussian and you cluster 4 different clusters, can 2 of them be better than the other 2?
Yeah, I'll show you the distribution. So that's exactly my coming slide to show the distribution before and after this quantization. this K-means quantization. So okay, I have one more question.
Why this method can get speed up, because in matrix multiplication, every time we want to get the number, it's an indirect address. We need to get the index first and then index it in the full group. So you have to access memory twice to get one number.
Yeah, so this requires specialized hardware support. So this is not in the main memory, but you can put it in the on-chip SRAM, since this is a pretty small code book, right? Which can be completed within one cycle to access 1 out of 4 numbers.
Yeah, so this method is not supported in general architecture such as CPU.
GPU or CPU. But recently, the NPU, there's one NPU that is actually supporting this called pilotization. The iPhone is possible utilizing these techniques. So specialized data path is required to support such technique. So let's see, how do we train to fine-tune the model if the weights are shared in such a manner? Okay, so we get the gradients out of this weight matrix. Okay, so these are the gradients corresponding to the same pattern. Okay? And then we group them by their indices. Okay, group them by color. We sum them up together. Okay? These are the summation of the gradients to change the centroid. And then we're going to multiply the learning rate subtracted from the original centroid. And then we will get the updated fine-tuned centroid in this manner. Okay, so this is the way to fine-tune such a weight shared neural net. And let's see how does accuracy go as we have fewer number of weights. Okay, so this is the laws of accuracy. We will not be this point, and this is the model size ratio after compression from 100% all the way to here at 8%. So if we do quantization, the accuracy is going to drop to roughly 12%, and it's going to accuracy is going to drop. So pruning only it's going to drop in a similar manner. And then the best way is to combine pruning and quantization together. So this is the compression ratio for LXNet. If we do pruning and then quantization, we can make it roughly 3 times of the original size. So here, let's brainstorm a little bit. Should we do pruning first and then quantization, or should we do quantization first and then do pruning? Pruning first. Yeah, pruning first. So you want to first reduce the number of weights, okay, and then you reduce the number of bits per width. Okay, so each weight you will have less number of bits, and then you have less number of parameters. These are orthogonal techniques. So let's see what happens to the weight distribution before and after quantization. Okay, so this is the weight distribution after pruning, which we have shown in the previous lecture, where everything near 0, they are removed. And after fine-tuning, the weight becomes smoother, right? So what happens after this quantization? The value becomes discrete. Then we have discrete values, but still the distribution roughly forms those 2 peaks, and there's very little weight in the middle. Okay, so after quantization, we have discrete weights. So it does answer the question. And then what about after fine-tuning? So the weights slightly shifted left or right. Okay, so this is before and this is after. We can observe these small changes of the location of the weight due to this fine-tuning, okay, to recover the accuracy after quantization. Okay. And let's see how many bits can we quantize before we lose accuracy. So here is the experiment. The experiment on the LXNet. Okay, so this is the convolution layer, and this is FC layer, fully connected layer. So for the convolution layer, as we are reducing the number of bits, okay, the accuracy begins to drop around 4 bits. Okay, so this is the top 5 accuracy. This is the top 1 accuracy. Okay. And we are showing 2 scenarios. One is quantized only. The other is pruned and quantized. It's showing that actually we can combine pruning and quantization, which give very similar results. Like this yellow versus this red, they are almost overlapping each other, showing that even after pruning, we can still quantize them to the similar number of weights, okay, above 4 bits. And below 4 bits, this quantized only, this pruned plus quantized, they start to differ a little bit. But in general, 4 bits, we lose very little accuracy. For the FC layer, we lose even less, right? So the accuracy is well maintained until we quantize them to only 2 bits, okay? Only 2 bits, which is making it very easy to store the weights in on-chip SRAM rather than having to go to off-chip. So after this weight sharing quantization, we find the weight distribution is not forming a is not uniform distribution. Some of the weights are very popular. Some of the weights are very not popular, right? So we want to represent those infrequent weights, using more bits to represent. And for those very frequently appearing weights, we can use a less number of bits to represent, right? So rather than using the same number of bits, 4 bits, 2 bits for all the numbers, okay, we want to use different number of bits to represent different numbers. Very popular one, we use less number of bits. Those less frequent ones, we use more number of bits. So overall, we can use this Huffman coding to further reduce the storage required to store those weights. Okay. So put them together, we have this deep compression pipeline that can drastically reduce the model size of neural networks. Refers to pruning, which make you have less number of weights, and then quantization have less number of bits per weight. And then finally, Huffman coding using different number of bits for popular versus infrequent weights. Okay. For pruning, we train the connectivity, prune it, and iteratively prune and fine-tune that. That can give you the same accuracy, but 9 to 13x reduction of the model size. And then quantization, we can first cluster the weights, like we color them into different colors, create a code book, and then we quantize the weights according to the code book and retrain the code book. In this manner, we can further improve the compression to 27 to 31 times. Finally, we encode the weights and index, okay, so that we can use different number of bits for popular versus infrequent weights, and finally lead to 35 to 49x reduction of the model size. So here is showing the compression results for several popular neural nets on the ANIMES versus on the ImageNet dataset. So ImageNet is probably more interesting. So AlexNet reduced from 240 megabytes to only like 7 megabytes. And the accuracy originally is 80.27, now is 80.3. Okay. So this result is 2016. So these days, even the top 1 accuracy, we can, our latest work called efficient VIT, we can easily get 80% top 1 accuracy rather than top 5 accuracy on ImageNet. So the area is moving super fast. So that could be a good example for you to do a final project to explore the modern neural nets. How does the pruning ratio look like, even for NLP models, for transformers, for vision transformers, etc. For VGG, originally it's super cumbersome, like 550 megabytes. So after compression, only about 11 megabytes. Okay, accuracy is still well maintained. GoogleNet, very efficient to begin with. Similarly for Redmond 18, they can be compressed less, but again, order of magnitude compression, only a couple of megabytes, very easy to fit on chip SRAM, so that you can avoid those off-chip DRAM access. Accuracy is also well maintained. And the interesting thing is that no matter how large they are to begin with, after compression, they're just roughly in the order of a couple of megabytes of model capacity. So the next question is basically, rather than compressing these models from large model to a small model, can we invent and design small and compact models to begin with? And whether such small model can be compressed after. So in order to explore this question, in collaboration with Berkeley, a couple of years ago, we designed a squeeze net. Okay, so the idea is that using this 1-by-1 convolution to squeeze the number of channels by a factor of 4 before we feed it with 3-by-3 convolution. Okay. And then we have these 2 branches to capture the information on different resolution, and then upscale the number of channels to 64 again before we feed it to the next layer. Okay. And this is showing the visualization is much deeper at that time. So as a result, this squeeze net is 510 times smaller than the original AlexNet, while maintaining the same accuracy. Okay, so let's look at this step by step. So squeeze net is originally much smaller, like 50x smaller than the original AlexNet, right? Only 4.8 megabytes compared with 240 megabytes. I think 50 times smaller and same accuracy. And still, such a model is still amenable to compression. After compression is only 0.47 megabytes, less than half a megabyte. Okay, while maintaining accuracy being 500 times smaller, okay, which is showing that even a small and compact model, you can still compress it, which is pretty exciting. So in two lectures, we are going to learn neural architecture search techniques that can automatically generate or synthesize neural network architectures that fit a particular model size constraint or latency constraint or flops constraint. Say you want a model that's exactly like 3.2 megabytes. How do we design such a model? Previously, you have to manually search, configure different channel number, different resolution, different width and depth. Now we have an automated tool to synthesize neural nets that can fit a target constraint. Okay. All right, so this is a summary for such K-means-based weight quantization, right? We have originally a 32-bit floating point number, and then we can store them in 2 parts. One is the code book, very small, 4 entries for 2 bits, 16 entries for 4 bits, and then we only store these integer indices. Okay? And during quantization, this ladder level indirection, where we have both the code book and quantized weights. We decode by referencing the code book to get the real floating point weights. And the weight and input are still calculated using floating point arithmetic. And added the files, that's the final output. Okay, so this is the computational graph. And in the next part, we are going to learn what if we don't have those floating point units at all? What if we only have those integer units? That's will be covered by the linear composition. Okay. So in the first half, we introduced this K-means-based quantization, which will be part of your homework assignment for lab 2, which is easy to implement, and also you can quantize that to lower number of bits. However, that requires specialized hardware support and specialized data path, since we need a level of indirection. And to make it simpler, we have this linear quantization techniques that can run on existing CPU and GPUs to achieve speed up. And let's see how does that work. Okay. So before jumping to the contents, there's a little bit of more math in this lecture. So hopefully get a little bit prepared. I will walk you through slowly. Feel free to raise any questions in the middle. Make sure you can follow the last half of the lecture. Okay. Okay, starting with the same matrix, floating point 4x4 matrix. Okay. What we are going to do is going to use those integer representation. Okay. We are going to have a code book. Now the code book is linear. Okay. This 0, 1 is indicating this 1, 0, 0 is 0, 1, 1 is -1, 1, 0, -2, using 2's complement representation, if you recall from 644. Okay. And then we are going to introduce this quantized weights represented in 2-bit signed integer. Okay, so this one actually is represented by 1. Okay? And then we introduce this 0 point. And this is another concept we newly introduced. We are going to learn how to determine that very soon. But just give you a high level idea, how does that work? We have a -0 point, and then scale them using a floating point number, okay, so that we can get a recovered matrix. Okay? So we are going to use this matrix for matrix multiplication for inference, and this is the quantization error. So the difference between the linear quantization versus K-means quantization is that these centroids, okay, they are linear. Okay, the distance between each centroid, they're equal. Okay, versus the previous one, remember we have 1, we have 1.5, we have -1, the distance is not equal. Okay, okay, so we have this equation where we want to have this linear projection from this integer weight to this floating point. Okay, so this is affine mapping of integers to a real number. Okay, from Q to R. Okay, from quantized to real. So we are going to use this notation throughout this lecture. So we are going to have this linear mapping by subtracting from a 0 point and scale it by a factor of s. Okay? So the s is a floating point number, which is a quantization parameter we can define ahead of time. And this z, this 0 point, is an integer number. Is again another quantization parameter we have to decide before the inference time, which allow a real number 0 to be exactly represented by the integer number z. Okay, so z will be mapped to 0. Okay, so this integer value z will be mapped to the value 0 in the floating point. So that's the function of this integer. We want to make sure there's some number that can be exactly representing 0. Okay, so z is actually representing the real number 0. That's the definition for this 0 point. Since 0 is very important, right? After pruning, we have so many zeros. We want to make sure some value, some integer value is actually representing the floating point 0. Okay, and what is that number? That is the z, the 0 point. Okay. So this is the mapping between the quantized value to the floating point number. So this is the actual number. This is the linear, integer representation for that. Okay. So let's introduce a few notations. Q-mean means given a certain number of bits. In this case, we have 8 numbers, 3 bits. Okay. This is the smallest value it can represent. This is the largest number it can represent. Using 3 bits. Okay. And R-mean is the smallest floating point number across this tensor. Okay. R-max is the largest number in this tensor. Okay. And so here, for the Q-mean and Q-max, for different bit width, we have different numbers. And for 2-bit width, actually this is reverse. Q-max and Q-mean. 1 minus 2, 3 minus 4, etc. You can correct the slides after the lecture. And then we are going to find this mapping between the Q-mean and Q-max. Put in the equation where we have this affine mapping where we are turning this quantized value to the floating point value. Q-max would be mapped to this R-max, right? So Q-max should be mapped to R-max. Q-mean should be mapped to R-mean. Okay, so in this case, we can calculate what is the scaling factor by subtracting these two equations. So intuitively, the scaling factor is the ratio between the dynamic range of the floating point number versus the range of this integer number. Okay, so we can calculate the scaling factor will be the distance between R-max and R-mean versus Q-max and Q-mean. Okay, so this is intuitive understanding. We are basically shrinking or growing the range by x. Okay. And how do we calculate that? So let's give an example. using our familiar weight matrix, 4x4 weight matrix, we are going to calculate the max, which is this number, 2.12. The mean is minus 1.08. We subtract them, which corresponds to the range with a floating point number. It's this blue range. Okay? And in the denominator is the range for this integer number. So here we are using only 2 bits. Okay? So the range is ranging from 1 to -2. So actually 3. Okay, so dividing these ranges, we can get the scaling factor is actually 1.07. Okay, so that's how we calculated this scaling factor. Okay? 1.07, which is distance between this largest and smallest number. Okay, in the floating point representation versus in the integer representation, this is the distance versus these two distances. And the ratio is basically this scale, 1.47. So far, so good. The step size of the integer.
Oh, yeah, it is always one, or is it constant, just constant?
It is always 1 since we are using the integer representation. Right. All right, then let's continue to talk about. So far we get how to get the s, right, the scaling factor, and then let's talk about how to get the other factor. Right, in F transformation, we have the scaling factor, we have a 0 point. Now let's calculate the 0 point. Okay, so remember we have this affine mapping between this quantized value to this real value. Okay, and let's just rotate the equation. We can easily get R mean divided by S, and then we move it to the right. And we can get the 0 point is actually Q mean minus R mean divided by S. Okay, which is basically saying we want to have this R mean shrink by the ratio, okay, and calculate the distance between Q mean and that ratio. Okay, so that we can get this Z, which is the 0 point. What is special? What is special for Z? Okay, among all these points, Z will be mapped to 0. Okay, so that's the definition of 0 point. Very simple math, but I want you to have the intuition, not only the math, but also the intuition. Z will be mapped to 0. And the calculation of that will be just round this value. Since we are using an integer, we want to make sure this is an integer. All right, so let's see in this example, how do we calculate Z equals to QB minus R mean divided by S. R mean is basically the smallest value in this weight matrix, which is minus 1.08. S is what we just calculated, 1.07. And Q mean, in this lookup table, the smallest number we have in integer representation is -2. Therefore, we calculate this number and round it, we get 1. Okay? In this case, this 1 in the integer representation will be mapped to 0 in the floating point representation. Okay. All right. So with that, we have enough knowledge to calculate how do we do a matrix multiplication in integer arithmetic on a computer with only integer arithmetic, and how do we do the matrix multiplication for a floating point neural net. So assume there's no bias for now, and then we're going to calculate what if we have bias. Okay, so as simple as y equal to w times x. W is the weight. It's pre-computed, it's a constant, and x is the input activation is dynamic. Okay, so we plug in this affine transformation. So let me move the screen a little bit so it's not shadowed. Okay, so we are going to have this equation throughout this section. Okay, so we plug in the W representation, which is scaling factor, QW quantized version minus the 0 point, where Z will be mapped to 0. Okay, and times the scaling factor of the input, okay, times the Q minus the 0 point of Q. And similarly for Y, we also plug in the quantized value. Next, we are going to continue by just calculate what is QY, right? So we are going to multiply this SW and SX together, divided by SY, okay? And these terms stay the same. Okay? And we also move the ZY from here to over there. Okay? I want you to make sure you understand this equation since we'll implement that in lab 2. And then we are going to expand these two terms. Okay? So two terms all together, we get 4 terms. Now we are going to take a careful look at these 4 terms, which are constant.
These are all matrices, right? So dividing by SY is just multiplying by the inverse, or
S is a scaling factor. It's not a matrix.
yeah, okay.
Yeah. All right. So we're going to first. This is just a number. It's not a matrix. And then this is a n-bit integer addition. And here it's an n-bit integer multiplication. Okay, since these are all integer values. But we want to do 32-bit accumulation to prevent this overflow. Okay. So these values, weight, remember weight is pre-computed, it's a constant. And 0 point is also constant. 0.01, they're both constant. Okay. So these can be pre-computed into one term. Okay. And for this number, the scaling factor, okay, we can actually represent this number by 2 to the power of n times a fixed point value. Okay, this value is between 0.5 and 1. So there is a very simple equation that can function in the library that can help you do such decomposition. So actually, you can use integer multiplication. So this is the integer. And then you can actually do bit shift, since 2 to the power of n can be easily implemented by shift, so that multiplying with this scaling factor even doesn't require a floating point arithmetic. So all integer arithmetic can deal with this problem. And so with that, let's continue the discussion. What about this ZW times QX? So ZW is the 0 point for the weights. Okay. And QX is not a constant, therefore we cannot pre-compute that. So how do we eliminate that? We see the distribution of the weight. Okay. Usually it forms roughly a normal distribution where the center is roughly around 0. So during quantization, to make the calculation easier, we just set this ZW to be 0. Okay. So that we can eliminate this term, this green term. Okay, by setting ZW to be 0, meaning that 0 in the quantized value will also be mapped to 0 in the floating point value, given the intuition that the weight distribution is roughly symmetrical. So let's see what happens if we set Z to be 0. So 0 will be mapped to 0. Okay, so this is the integer representation. This is the floating point representation. Now the 0 point are aligned. Previously, it's not aligned. Okay. So let's see the dynamic range. Okay, if we have full dynamic range, there are 2 ways to calculate the scaling factor in this case. So remember, the scaling factor is defined as the ratio between the range of the original floating point dynamic range versus the integer's dynamic range. Okay. And we can also use this equation to calculate the dynamic range to be R mean divided by Q mean minus Z. In this case, if Z is 0, then we can directly calculate that by minus R max versus Q mean, which is minus R absolute value max versus divided by Q mean. Okay. So this is PyTorch native implementation and also Onyx implementation. The tricky part here is that we have even number of centroids, right? In this example, we have 8 centroids, but one of them is 0. Therefore, the negative and the positive, they're unequal, right? We have 3 positive values, 1, 2, 3, but 4 negative values, right? So which one should we have for the range? The first method, we are using the R mean to the Q mean to calculate the range. Okay, and in the next slide, we can also use the Q-max to calculate the range. Okay, since we have uneven number of positive and negative number of centroids. Okay, so if we use this Q-max and R-max to calculate the range, so that will be R-max divided by Q-max. Compared with the previous example, they're using that divided by the Q-mean. So they differ slightly a little bit, 3 versus 4. Okay, but this is the method that is used by TensorFlow, by NVIDIA TensorRT, and Intel libraries, etc. Okay, those are some of the details. Okay, so in the high level, we have this asymmetric linear quantization, meaning that the 0 point is not 0. You are mapping a non-zero number to a 0. Okay. But the symmetric linear quantization is saying that 0 will be mapped to 0. Okay. From this integer value 0 will be mapped to the floating point value 0. So there are pros and cons for both approaches. Okay, so for the asymmetric, the quantized range is fully utilized, right? So the whole range for the integer value, the whole range for the floating point value. And the implementation is more complex. Of course, you have this z value, and 0 point requires additional logic in hardware. Okay, and for symmetric representation, not all the weights are symmetric, and activation is not symmetric, especially when you have this random activation function, right? When you're quantizing the activations, you assume 0 will be mapped to 0. Then you are wasting half of the range, since after value, there's no negative number, but you still dedicated a few centroids to represent those negative numbers. But after value, you only have a positive number. So that's the problem of wasting, wasting one bit effectively by using such symmetric linear quantization. Okay. But the advantage is that the implementation is much simpler. Okay, since we can get rid of this term, which is ZW is 0. Okay, 0 will be mapped to 0, so 0 point of W of the weight is 0. And also for the activation, no matter what it is, since it's dynamic, we can get rid of that term, which will simplify our equation to be this scaling factor of weight, activation, and the output. And we have this also for the additional 0 point for the y, we can have this term. Okay. So now we have only one last thing to solve, which is the bias. Just now we calculated whether we don't have bias, it's y equal to wx. Now we have wx plus b. How do we handle the bias in the neural network? These are the constants. So again, we plug in the mapping, okay, minus the bias, 0 point of the bias, and then times the scaling factor of the bias. Okay, since they can be trained together, so if you change the scaling factor, you can stay constant by manipulating the Q bias as well, since both of them are constant. Two constants multiplied together to make this larger or make this smaller. Okay, so just like before, we set ZW to be 0. Okay? So we can greatly simplify that by setting this ZW to be 0. So here we have only these two terms by getting rid of this ZW and distribute this QW to QX and ZX, right? And combine SW and SX. So it is here. And then we have this a couple of remaining terms we can deal with, right? In order to merge these two terms together, remember this S and Q, this is the bias, this is the scaling factor, they're both constant. So two constants multiplied together, you can set one of them to be an arbitrary value. So you can adjust the other one accordingly, right? So in order to merge them together, we set SB to be equal to SWSX, right? So we set SB to be the same as SW times SX, so that we can further simplify the equation by merging this QB into this equation, right? And also we set ZB to be 0 again, right? With the 0 point of the bias should be also 0. Okay. So let's see this again. We have these two terms, we follow as before, and then we have this 2B becomes here, since the SB becomes the same as SW as X. This is the last complicated equation, so make sure we are on the same page, right? Go back a little bit. We first assume ZW to be 0, right? Since the weight distribution is symmetric, we map 0 to 0. And then we set ZB to be 0 again. For the bias, also is symmetric, so we set 0 to map to 0. And then we set the scaling factor for the bias to be the same as the modification of the scaling factor of the weight and the division, so that we can combine the term in this format. So far, so good. Yeah, question.
I feel like I'm missing a key bit of intuition. So I know, so y equals wx is matrix multiplication.
Correct.
And then all these equations with s's are all integers. So how is it? Is like each integer equation here like mapping to like one element of the matrix, or how is it representing the matrix multiplication? It's all
So this is matrix. This is matrix. Okay, so this is also the scaling factor is not a matrix. The scaling factor is just a value.
Oh, so Q and Z are matrices.
Yeah, Q and this QX, this QW, and this QB, they are matrices. And Z is a constant. It's a value.
So
Okay. It's a bias, element bias. Yeah. Okay, we're almost there. So we have these three assumptions, and then we can further simplify the equation in this manner. So we put this QSY to the right, and then we can have the final representation to be like this. So the output will be this combined scaling factor, and then W times X. These are all constants, so we can pre-compute them. Okay, and also we define this Q bias to be QB minus this term. Okay, so we can further simplify that by plugging Q bias instead of this yellow part. Okay, and then by examining the current representation, we get a very simple form. Okay, so the output is a scaling factor times the weight times the activation in matrix multiplication or convolution, whatever you have, and then plus the Q bias, which is defined using this equation, okay, plus the ZY, the 0 point of the activation. So we can calculate that by pure integer multiplication. Okay, so all these are integers. Okay, and then we can rescale that to integer and then shift it. Okay, and finally add the n-bit integer bias. That is matrix multiplication. So what if we have convolution? It's very similar. We just replace this matrix multiplication with a convolution. Okay, so that solve the problem for convolutional neural nets as well. So let's see the computation of RAG. So we have to quantize the inputs and quantize the weights. This is the constant. Okay, so they are both integer. We do an integer convolution on top of this weight and activation. We get an integer output. We add this quantized bias, okay, and accumulate that in 32-bit floating point to prevent this overflow. Okay, and then we multiply it by the scaling factor. The scaling factor multiplication will be also done by integer followed by a shift. Okay, and then we add the 0 point. Okay, at the 0 point of the y, and finally we get the quantized output, which can be fed to the next layer. And the intuition behind this scaling factor is that it basically contains 3 terms: the weight, activation, and the output. Okay, so that makes sure the output is still can be directly fed to the next layer.
So how do you determine the 0 point of y?
For y, you observe the distribution. You want to feed the neural net with like 100 or 500 images and compute the statistics. That's called calibration.
So also the SY and
in that way as well. Yes. All right, so this is showing the improvement compared with using floating point versus 8-bit integer. What is the latency versus what is the accuracy, right? So with the same accuracy, we can reduce the latency from 50 milliseconds to about 5 milliseconds, which is showing the speed up and also the improvement. For the accuracy compared with floating point, what we have introduced just now, there's a little bit of loss of accuracy. This is in the 2018. So nowadays, there are more advanced techniques that can do such post-training quantization where fine-tuning, weight equalization, etc., which we'll cover in the next lecture to bridge the gap. So nowadays, we can pretty much fully bridge the gap by using 8-bit integer to have the same accuracy of the floating point accuracy for both weights and activations. All right, so we learned K-means quantization and also the linear quantization. We went through all the equations, and now basically you have an idea how to calculate the bias, how to calculate the scaling factor. And in the next lecture, we are going to cover more aggressive quantization techniques like binary or ternary representations. Okay, so here's a that's a question. Oh, no question. Okay, good. So here's a summary for today's lecture. We first review those data types. What is IP32 brain float? What is tensor float? 32, what is IP half precision, full precision? And then we learned the basics of quantization, including K-means quantization, and also the linear quantization. Okay, that's all for today's lecture. Thank you so much, and hope you have a good weekend.